624 trillion miles from Earth, James Webb stared at a dim red star and found a chemical whisper that should not be easy to ignore. Not a city, not a signal, not a spacecraft drifting through the dark. Something stranger. A distant world, larger than Earth, wrapped in hydrogen, possibly hiding a planet-wide ocean, showed hints of molecules that on our world are tied to living things. And the reason astronomers went quiet is simple. This is not Mars, not Europa, not a moon in our own backyard. This is a world more than 120 light-years away, orbiting another star entirely. And Webb may have caught the atmosphere of that world, carrying the first faint suggestion that biology is not unique to Earth. We are going to travel through this discovery, layer by layer, from the first odd spectrum to the chemistry that made scientists hesitate before saying a single dramatic word out loud. If you enjoy serious space stories built on real science, subscribe, because what comes next is one of the strangest investigations astronomy has ever opened. It started with a dip in starlight that did not look ordinary. The planet is called K-18b. It orbits a red dwarf star in the constellation Leo, about 124 light-years from Earth. That distance sounds close by galactic standards. It is not. Light, moving at 186,000 miles per second, still needs more than a century to cross that gap. That means every photon web collected from this system began its journey while human beings were still in the early 20th century. Before satellites, before moon landings, before anyone knew planets existed around other stars at all. And yet Webb was not looking directly at the planet. That detail matters. Exoplanets, like K-18b, are usually too small and too lost in the glare of their stars to photograph cleanly. So astronomers use a different method. They wait for the planet to pass in front of its star. During that transit, a tiny fraction of the starlight filters through the planet's atmosphere before reaching the telescope. Molecules in that atmosphere absorb specific wavelengths. They leave gaps in the light. A pattern, a fingerprint. That fingerprint is where the story begins to turn. Because K-18b did not look like a simple rocky planet. It did not look like a straightforward gas giant either. Its radius is about 2.6 times Earth's. Its mass is about 8.6 times Earth's. Put those together and you get a world with a lower density than Earth, one that likely contains either a huge volatile rich interior, a deep atmosphere, or both. Too big to be called Earth-like, too small to be comfortably grouped with Neptune, sitting in the awkward middle ground where the universe likes to build things we do not yet fully understand. Now consider the scale of that uncertainty. Earth's atmosphere is a thin skin around a rocky world. The deepest ocean trench on Earth is a scratch compared to what a so-called Hycean planet might host. If K-18b really is what some models suggest, then beneath its hydrogen-rich atmosphere could sit an ocean far deeper than all of Earth's oceans combined. No continents, no shorelines, no blue marble with clouds drifting over visible land, just atmosphere, pressure, darkness, and perhaps a global ocean stretching downward into depths no human submarine could survive. That comparison matters because K-18b is often placed beside Europa, Enceladus, and Titan. But the resemblance is partial, not complete. Europa likely hides a salty ocean beneath ice. Enceladus sprays water vapor and organics through cracks in its crust. Titan has methane weather and chemistry rich enough to keep astrobiologists awake at night. Those are icy worlds in our own solar system. K-18b is something else. Larger, warmer, wrapped in hydrogen, possibly ocean-bearing, but under conditions that may be more alien than anything nearby. It is less like finding a second Earth and more like finding an entire new category of habitable possibility. Here is where it gets strange. When Webb analyzed the atmosphere, astronomers found strong evidence for methane and carbon dioxide. That alone was important. Methane is a simple carbon-bearing molecule. Carbon dioxide is another. Together, in a hydrogen-rich atmosphere, and with ammonia apparently depleted, they fit one possible picture of a Hycean world, a planet with an ocean below and chemistry above that may be consistent with habitability in at least some layers. Not proven habitability, not confirmed oceans, but a world that suddenly moved from interesting to urgent. Then came the weaker hint, a possible signal from dimethyl sulfide, DMS. On Earth, dimethyl sulfide is overwhelmingly associated with life, especially marine microorganisms, such as phytoplankton. That does not make it a guaranteed biosignature everywhere. Chemistry is dangerous that way. A molecule familiar in one world can mislead you on another. But when a possible DMS signal appears on a world that may have a vast ocean, scientists pay attention, carefully, quietly, and with the kind of skepticism that real discoveries require. Remember that detail, because it becomes important now. The first DMS hint was not strong enough to justify dramatic conclusions. It was exactly the kind of signal that can dissolve under better data. Instrument noise, model bias, overfitting, a missing molecule in the comparison set. Astronomy has been humbled before, so the response was not celebration, it was repetition. Webb had to look again, and that second look changed the tone of the conversation. Using a different wavelength range, researchers reported a new signal in 2025 that they argued could be explained by dimethyl sulfide and possibly dimethyl disulfide, another sulfur-bearing molecule with potential biological relevance. The statistical significance was stronger than before, around the level where scientists stop treating a result as random noise and start treating it as something that deserves a serious fight. Not a victory, a fight, because once the result appeared, so did the pushback. Other teams reanalyzed the broader spectrum and argued there was still insufficient evidence for DMS or DMDS. Some pointed out that other molecules with similar spectral features could mimic the signal. Others questioned whether K-18b is even the kind of ocean world people hope it is. There are models in which it is more like a mini Neptune with a deep hydrogen envelope and no accessible liquid ocean at all. There are models where high-pressure water layers or supercritical fluids replace any Earth-like sea entirely. That is the core of the mystery. James Webb may have detected possible signs of life on a distant ocean world, or it may have detected chemistry on a world that only looks habitable from far away, or it may have detected molecules that are real but not biological. 3 possibilities, all still alive, all still on the table. And what comes next is the part that makes this story bigger than a single planet. Why this combination of molecules matters, why methane plus carbon dioxide plus a sulfur-bearing gas gets astronomers thinking about metabolism, and why the most difficult question in the entire search for life is not, did we detect something, but what else could make it? The combination is the signal, not any one molecule on its own. Methane exists in many places. It forms in gas giants. It leaks from geological processes. It appears in comets and interstellar clouds. Carbon dioxide is even more common. It is one of the baseline gases of planetary atmospheres. If Webb had only seen those two, the story would have ended quietly inside research papers. But chemistry is not just about presence, it is about coexistence. Methane and carbon dioxide together in a hydrogen-rich atmosphere suggest a system that is not in simple equilibrium. On a planet left alone long enough, chemistry tends to settle. Reactive gases combine, break apart, and eventually reach a balance dictated by temperature, pressure, and available energy. When you see molecules that should not comfortably coexist without constant replenishment, you are looking at a system being driven. Something is feeding it. On Earth, that something is life. Marine microorganisms produce dimethyl sulfide as part of their metabolic cycle. They take in nutrients, process sulfur compounds, and release DMS into the atmosphere. It rises, interacts with sunlight, contributes to cloud formation, and becomes part of a planetary-scale feedback loop. That loop is not random, it is structured, it is sustained. Now consider K2-18b again. A possible ocean world, a hydrogen-rich atmosphere, methane present, carbon dioxide present, and a tentative signal of a sulfur-bearing molecule that, on Earth, is tightly linked to biological activity. Individually, each piece is explainable. Together, they form a pattern that is difficult to ignore, but difficult does not mean definitive. Here is where the investigation becomes technical. Webb does not see molecules directly, it sees absorption lines. When starlight passes through an atmosphere, specific wavelengths are absorbed depending on which molecules are present. These appear as dips in the spectrum. Each molecule has its own pattern. Methane absorbs in certain infrared bands, carbon dioxide in others. Dimethyl sulfide has its own signature, but that signature can overlap with other compounds, especially in noisy or incomplete data. That overlap is the battlefield. Scientists build atmospheric models. They simulate thousands of possible compositions. They compare those models to the observed spectrum and calculate which combination of molecules best fits the data. But the process is not perfect. If a model is missing a molecule that actually exists in the atmosphere, it might incorrectly assign that spectral feature to something else. If the data is noisy, small signals can appear or disappear depending on assumptions. That is exactly what happened here. The initial Webb observations used one instrument mode. The follow-up used another, extending the wavelength range and improving sensitivity in certain regions. The second dataset suggested a stronger case for sulfur-bearing molecules, but even then, the signal sits at a level where interpretation matters as much as measurement. One team sees DMS or DMDS, another sees ambiguity, and that tension is not a flaw. It is the process working correctly. Now consider the scale of what Webb is doing to produce this data. The planet blocks only a tiny fraction of its star's light during transit. The atmospheric signal is an even smaller fraction of that. We are talking about variations measured in parts per million. Imagine trying to detect a single drop of dye in an Olympic swimming pool from more than 100 light-years away, using a mirror floating in deep space. That is the level of precision required. Webb achieves this through its infrared instruments, particularly NIRSpec and NIRIS. These instruments disperse incoming light into spectra with extraordinary sensitivity. They operate in a temperature-stabilized environment at the Lagrange 2 point, about 1.5 million kilometers from Earth, shielded from solar radiation by a multi-layer sunshield. The entire system is designed to detect faint infrared signals without thermal interference. Because infrared is the key, many of the molecules relevant to life absorb strongly in infrared wavelengths. Visible light would miss them entirely. Webb's ability to observe in the infrared is what allows it to probe exoplanet atmospheres in the first place. Without that capability, K2-18b would remain a distant point of light with no chemical identity at all. But even with that capability, interpretation remains the challenge. Here is where it gets more complicated. There are non-biological pathways that can produce methane. Geological processes, such as serpentinization, where water reacts with certain rocks, can generate methane without life. Photochemistry in hydrogen-rich atmospheres can also produce methane under certain conditions. Carbon dioxide is even less diagnostic. It forms easily and persists. The real question is whether dimethyl sulfide or dimethyl disulfide can be produced abiotically in significant quantities on a planet like K2-18b. On Earth, the answer is essentially no, but Earth is not a hydrogen-dominated Haitian world. Some theoretical studies suggest that under high-pressure, high-temperature conditions with different atmospheric chemistry, sulfur-bearing organic molecules could form without biology. The rates, however, are uncertain. The pathways are not well constrained. And crucially, the combination of all three signals together is still difficult to reproduce without invoking some kind of sustained chemical disequilibrium. That word matters, disequilibrium. Life is, at its core, a process that maintains disequilibrium. It takes energy from its environment and uses it to create and sustain chemical states that would otherwise collapse. Oxygen in Earth's atmosphere is a classic example. It should react away. It persists because life constantly replenishes it. Methane behaves similarly. It is unstable over long timescales in an atmosphere exposed to radiation. If you see it in large quantities, something is making more of it. Now imagine that process happening on a world 124 light-years away. Not proven, not confirmed, but suggested. And that suggestion pushes this discovery into a broader context. The Drake equation. Frank Drake's equation was never meant to give a precise number of civilizations. It was a framework, a way to break down the problem of life in the universe into factors: the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, the probability of life emerging, the probability of intelligence, and so on. For decades, one of the biggest uncertainties in that equation has been the fraction of habitable worlds that actually develop life. We did not know how common such worlds were. We did not know if Earth was typical or rare, and we had no way to probe the atmospheres of distant planets in detail. Webb changes that, not by answering the equation, by turning one of its terms from speculation into measurement. K2-, 18b, is not Earth, but it sits within the habitable zone of its star, the region where temperatures could allow liquid water under the right conditions. Its size suggests it may host environments very different from our own, but still potentially stable over long periods. If molecules associated with life can be detected in its atmosphere, even tentatively, then the number of candidate life-bearing worlds in the galaxy may not be small. But that conclusion is still ahead of the data, because before we expand the equation, we need to understand the planet itself. And that is where the mystery deepens again. What exactly is K2-, 18b? One model suggests a Hycean world, a planet with a deep global ocean beneath a hydrogen-rich atmosphere. In this scenario, the atmosphere acts as a blanket, trapping heat and allowing liquid water to exist even at distances where a purely rocky planet might freeze. Another model suggests a mini Neptune, a planet with a thick envelope of gas, high pressures, and no clear boundary where a liquid ocean could exist in a way compatible with life as we understand it. The difference between those two models is everything. In the Hycean scenario, there could be a vast ocean interacting with the atmosphere, chemical exchange between water and air, potential niches where life could emerge and sustain itself. In the mini Neptune scenario, the atmosphere becomes so thick and the pressure so extreme that any water present may exist in exotic phases, supercritical fluids, high-pressure ices, environments far removed from anything we would call habitable. The data does not yet choose between them cleanly, and that uncertainty feeds directly back into the interpretation of the molecules. Because if there is no ocean, then biological explanations weaken. If there is an ocean, they gain strength. This is the kind of loop that defines modern astronomy. Observation informs models. Models reinterpret observation, and the answer sits somewhere in the tension between them. Webb's next observations are designed to break that loop. Longer observation times, broader wavelength coverage, higher signal-to-noise ratios. Each new dataset reduces uncertainty, narrows the range of possible atmospheric compositions, and either strengthens or weakens the case for specific molecules. Future telescopes will push even further. The extremely large telescope, currently under construction, will be able to perform high-resolution spectroscopy from the ground. The Nancy Grace Roman Space Telescope will survey wide fields and potentially identify more planets like K2-, 18b. Together, they will build a statistical picture rather than relying on a single example, because one planet is not enough. Even if K2-, 18b turns out to host life, it would not answer the deeper question of how common life is. It would simply prove that life can emerge under more than one set of conditions, and that alone would change everything. But we are not there yet. Right now, we are in the phase where every explanation must survive scrutiny. Abiotic chemistry must be ruled out or shown to be insufficient. Instrumental biases must be tested. Alternative molecules must be considered. The planet's structure must be constrained. Only after all of that can anyone begin to use the word life without qualifiers. And even then, it will not be a single announcement. It will be a convergence. Multiple observations, multiple instruments, multiple teams arriving at the same conclusion from different angles. That is how discoveries of this magnitude become real. And until then, the signal remains what it is: a whisper, a distant atmosphere carrying molecules that, on one world we know well, are tied to living systems, a planet that may or may not have an ocean, a dataset that refuses to resolve cleanly into a single explanation, and a telescope 1.5 million kilometers from Earth, continuing to collect light that left its source before modern astronomy even existed. The next piece of evidence is already on its way. The next piece of evidence does not come from a new molecule. It comes from time. Every transit of K2-18b across its star is an opportunity. The planet passes in front, the starlight filters through its atmosphere, and Webb records another spectrum. Each pass adds more data. Each pass sharpens the signal, and with enough repetitions, patterns either strengthen or disappear. That process is slow by design. K2-18b takes about 33 Earth days to orbit its star. That means usable transits are spaced out. Not everyone is observable. Not everyone is clean. Stellar activity, instrumental limits, scheduling constraints, all of it reduces how often Webb can collect ideal data. So the investigation unfolds over months, then years, and that delay matters because the atmosphere itself may not be static. On Earth, atmospheric composition changes with seasons, biological cycles, ocean activity, and solar radiation. If K2-18b has a dynamic atmosphere, and there are reasons to think it might, then its chemical signature could vary over time. Methane levels could fluctuate. Sulfur compounds could rise and fall. Cloud layers could obscure or reveal different spectral features depending on temperature and circulation patterns. Now imagine trying to detect life through that moving target. Not a single snapshot, a system. This is where Webb's repeated observations become more than confirmation. They become a way to track behavior. If dimethyl sulfide or any candidate biosignature appears consistently across multiple transits in different observational modes under different stellar conditions, the case strengthens. If it fades or disappears, the interpretation changes. If it shifts in intensity, scientists begin asking not just what is there, but what is changing. And that brings in another layer. The star itself. K2-18 is a red dwarf, smaller and cooler than our Sunday, but more active in certain ways. Red dwarfs can produce flares, bursts of radiation that impact planetary atmospheres. Ultraviolet radiation from these flares can break apart molecules, drive chemical reactions, and reshape atmospheric composition over time. So when Webb detects methane or a sulfur-bearing molecule, it is not just measuring what exists, it is measuring what survives. If methane persists despite stellar radiation that should break it down, then something must be replenishing it. If sulfur compounds appear in a stable pattern, then something must be producing them continuously or frequently enough to maintain their presence. That something is the central question, and this is where the concept of metabolism enters the conversation, not as a conclusion, but as a framework. Metabolism, in its simplest form, is a system that converts energy into chemical work. On Earth, different life forms use different pathways. Some use sunlight, some use chemical gradients. Some live in deep ocean vents, feeding on sulfur compounds in complete darkness. That last detail matters more than it seems, because if K2-18b hosts an ocean, it would likely be shielded from direct stellar radiation by a thick atmosphere. Light penetration could be minimal. If life exists there, It may not resemble surface photosynthetic organisms at all. It may resemble Earth's deep-sea ecosystems, where life thrives without sunlight, driven by chemical energy. In such environments, sulfur chemistry plays a major role. Hydrothermal vents on Earth release sulfur compounds. Microorganisms use them as energy sources. Byproducts of those processes can include molecules like dimethyl sulfide. That connection is why DMS, even as a tentative signal, draws so much attention. Not because it proves life, because it fits into a known biological pathway. But here is the part that makes scientists cautious. We only have one example of life. Every biosignature we recognize is based on Earth. Every assumption about what life produces, how it behaves, and what it leaves behind is drawn from a single data point. That creates a bias, a powerful one. It is possible that life elsewhere uses entirely different chemistry. It is also possible that non-living systems can mimic the chemical patterns we associate with biology. That is why the phrase possible biosignature is used so carefully. It acknowledges the pattern without claiming the cause, and the cause is what matters. Now consider how scientists try to separate those possibilities. They do not look at one molecule, they look at networks. A biosignature is stronger when it appears as part of a system of molecules that collectively indicate disequilibrium. Methane plus carbon dioxide plus a sulfur compound is more compelling than any one of those alone. Add in the absence of other expected molecules like ammonia, and the picture becomes more specific. Because ammonia in a hydrogen-rich atmosphere should be present if nothing is removing it. Its absence suggests that something is altering the chemistry. That something could be photochemical processes driven by the star. It could be interactions with an ocean. It could be unknown atmospheric dynamics. Or, in the most speculative interpretation, it could be linked to biological processes. Each explanation makes predictions. Photochemistry predicts certain byproducts and ratios. Ocean-atmosphere interactions predict others. Biological systems, if they exist, would produce patterns that differ in specific, testable ways. Webb's job is not to decide which is correct. It is to collect enough data that one explanation survives better than the others. And that process extends beyond Webb alone. Multi-wavelength observations are now part of the investigation. Different telescopes see different parts of the spectrum. By combining data across wavelengths, scientists can build a more complete picture of the atmosphere. Some molecules absorb strongly in one band and weakly in another. Overlapping observations help disentangle which signals belong to which compounds. Ground-based telescopes are also being used to monitor the star's activity. Understanding how often K2-18 flares, how intense those flares are, and how they interact with the planet's atmosphere is critical. Without that context, atmospheric signals can be misinterpreted. Because a flare-driven chemical reaction can mimic a biosignature, that possibility has to be tested and ruled out. At the same time, atmospheric modeling is becoming more sophisticated. Instead of assuming simple, static atmospheres, researchers are building three-dimensional models that simulate circulation, temperature gradients, cloud formation, and chemical reactions over time. These models can produce synthetic spectra predictions of what Webb should see under different conditions. Those predictions are then compared to the actual data. If a model reproduces the observed spectrum without invoking biology, it weakens the biosignature case. If no abiotic model can reproduce the data convincingly, the biological interpretation gains weight. That is the direction this field is moving. Not toward a single discovery, but toward a process of elimination so thorough that only one explanation remains viable. And even then, caution remains, because the stakes are not just scientific, they are conceptual. If life exists on K2-18b, or on any exoplanet detected through atmospheric chemistry, it would mean that life is not confined to a narrow set of conditions. It would suggest that the universe produces living systems under a wider range of environments than previously assumed. That would shift the Drake equation in a fundamental way. The fraction of habitable worlds that develop life would no longer be an unknown bounded by a single example. It would become a measurable quantity, and if that fraction is not vanishingly small, then the galaxy may be filled with worlds where chemistry crossed the threshold into biology. But there is a second implication. Distance, K 2 negative 18b, is 124 light-years away. Even if life exists there, even if it is confirmed beyond doubt, it is not reachable, not with current technology, not with anything on the near horizon. The discovery would expand knowledge, not access. It would answer a question, but not remove the separation. And that separation changes how the discovery is experienced. It becomes less about contact and more about context. We would not be alone in principle, but we would remain isolated in practice. That distinction is easy to overlook. Now step back to the present moment. The data is incomplete. The molecules are tentative. The models are competing. And the signal, whatever it represents, is still being tested. What comes next is not a single announcement. It is accumulation, more transits, more spectra, more analysis, more debate. The kind of process that takes years and resolves into something that, when it finally arrives, feels almost inevitable in hindsight. But right now, it is not inevitable. It is uncertain. And that uncertainty is where the story lives. Because the universe is not offering a clear answer. It is offering a pattern, a distant world with chemistry that does not settle into something simple, an atmosphere that may be interacting with something below it, a signal that could be biological, could be geological, or could be something entirely unexpected, and a telescope that continues to watch, collecting photons that began their journey long before we had the tools to understand them. The next observations are already scheduled. The next data sets are already forming, and somewhere inside those incoming photons is either confirmation, contradiction, or something no one has predicted yet. The next layer of the investigation is not about what was detected. It is about what should have been there, but wasn't. Because absence, in atmospheric chemistry, can be as revealing as presence. When scientists model a hydrogen-rich atmosphere like the one expected on K 2 18b, they predict a set of baseline molecules. Methane, yes. Water vapor, under the right conditions. Ammonia, in measurable quantities. These are not exotic predictions. They are the natural outcomes of known chemistry under pressure, temperature, and radiation levels consistent with a sub-Neptune-sized world. But when Webb looked, ammonia was not clearly present. That detail did not dominate headlines. It sat in the background of the data, quiet, technical, easy to overlook, but inside the research teams, it became one of the most discussed features of the entire observation, because ammonia should survive in a hydrogen-rich atmosphere unless something is removing it. Photochemistry can destroy ammonia. Ultraviolet radiation from the star can break it apart, but that process leaves fingerprints, byproducts, ratios between molecules that can be modeled and compared to observation. Ocean-atmosphere interaction can also remove ammonia. If there is a large body of liquid water beneath the atmosphere, ammonia can dissolve into it. That would reduce its atmospheric concentration and potentially align with the absence Webb observed. Now consider what that implies. If ammonia is missing because it is dissolving into a global ocean, then the Hessian model gains strength. The planet is not just a gas envelope. It is a system where atmosphere and ocean exchange chemicals, a system where the surface, or what passes for a surface, is actively interacting with the air above it. That interaction is a prerequisite for many biological processes, but it is also consistent with purely physical chemistry. This is the tension again. Every clue supports multiple interpretations, and this is where scale returns to the story. Because when we say ocean, we instinctively think of Earth, shallow by cosmic standards. The deepest point in Earth's oceans, the Mariana Trench, reaches about 11 kilometers below sea level. That is enough to crush submarines, enough to push pressure beyond what most materials can handle. But on a world like K2-18b, if an ocean exists, it could extend far deeper, hundreds of kilometers, perhaps more, under pressures that change the behavior of water itself. Not liquid in the familiar sense, but phases that blur the boundary between liquid and solid. Supercritical fluids, high-pressure ices that form beneath layers of liquid water, environments where the chemistry we understand begins to shift. Now imagine life in that context, not surface-dwelling organisms exposed to sunlight, but systems operating in darkness, under pressure, driven by chemical gradients rather than photons. Life that may not resemble anything on Earth's surface ecosystems, but perhaps shares more with the organisms found near hydrothermal vents, deep beneath our own oceans. Those environments on Earth are isolated, extreme, and yet full of biological activity. They do not rely on sunlight, they rely on chemistry. And chemistry is exactly what Webb is detecting. Here is where it gets more precise. If K2-18b has an ocean interacting with its atmosphere, then gases produced in that ocean could rise upward. Methane, produced either biologically or geologically, could accumulate in the atmosphere. Sulfur compounds, if generated, could follow similar pathways. The atmosphere becomes a window into processes happening far below. But that window is distorted, because before any molecule reaches Webb's detectors, it passes through layers of atmosphere, interacts with radiation, mixes with other compounds, and is shaped by temperature gradients and winds. What Webb sees is not the source, it is the result, and reconstructing the source from that result is one of the most difficult, inverse problems in science. Now consider the statistical side of the detection. When scientists report a signal at around 3 sigma, they are saying that the probability of the signal being due to random noise is low, but not negligible. It is a threshold where attention is justified, but certainty is not. 5 sigma is the standard for discovery in many fields. That corresponds to a probability of error so small that it is treated as effectively zero. The DMS or DMDS signal has not reached that level, which means the current state of the evidence is exactly where caution is required. Not because the signal is weak, because it is strong enough to matter, but not strong enough to conclude. And that intermediate state is where most real discoveries live for a long time. Now bring in the broader population of exoplanets. K2-18b is not unique in size. Sub-Neptune and super-Earth planets are among the most common types of planets detected in our galaxy. That alone is significant. It means that whatever K2-18b is, there are likely millions of similar worlds. But we have not been able to probe their atmospheres in detail until now. Webb is changing that. Each new observation adds to a growing catalogue. Some planets show water vapor, some show clouds that obscure deeper layers, some show simple molecules, and now, possibly, some show more complex chemistry. If patterns begin to repeat, if multiple worlds show similar combinations of gases, then the interpretation shifts. Because a single anomaly can be explained away, a population cannot. That is why follow-up targets are already being prioritized. Planets similar in size, temperature, and stellar environment to K2-18b are being scheduled for observation. The goal is not just to confirm this one case, but to see whether it is an outlier or part of a broader class. If multiple Haitian candidates show methane, carbon dioxide, and sulfur-bearing molecules, then the question changes. It becomes less about whether one planet hosts life, and more about whether a certain type of environment tends to produce certain chemical signatures. And that is how science moves from anecdote to pattern. Now, step into the theoretical side again. There are proposed abiotic pathways for sulfur-bearing molecules in hydrogen-rich atmospheres. Some involve photochemical reactions driven by ultraviolet radiation. Others involve high-temperature processes deeper in the atmosphere or interior. But these pathways often produce additional byproducts, molecules that Webb can, in principle, detect. So the presence or absence of those byproducts becomes a test. If Webb sees DMS, but not the expected accompanying compounds from an abiotic pathway, that pathway becomes less likely. If it sees the full set, the biological interpretation weakens. This is the logic of elimination, and it is why the next observations are so important, because they are not just looking for confirmation, they are looking for context. Now consider another constraint: temperature. K2 18b receives less stellar energy than Earth does from the Sun, but its thick atmosphere could trap heat efficiently. Models suggest surface or near-surface temperatures that could allow liquid water under certain conditions. But those conditions depend on atmospheric composition, pressure, and cloud coverage. Clouds, in particular, complicate everything. They can obscure spectral features, reflect radiation, and alter temperature profiles. A cloudy atmosphere can hide molecules from detection or mimic the presence of others by changing the way light passes through it. Webb's data includes hints of clouds or hazes in K2 18b's atmosphere, which means the signals we are interpreting are filtered through an additional layer of uncertainty. Again, the pattern repeats. Every answer introduces another variable, and yet, despite all of this complexity, the core observation remains: a distant world, an atmosphere containing methane and carbon dioxide, a tentative signal of sulfur-bearing molecules, a missing molecule that should be there, and a system that does not settle into a simple equilibrium state. That combination is what keeps scientists focused on this planet, not because it proves life, because it resists easy explanation, and that resistance is what drives investigation. Now shift to the broader implication. If K2 18b or any similar planet does host life, then the conditions required for life may not be as narrow as once thought. Life may not require a rocky surface. It may not require direct sunlight. It may not require Earth-like atmospheres. It may emerge in environments dominated by hydrogen under pressures and temperatures very different from our own. That possibility expands the habitable zone concept. Traditionally, the habitable zone is defined by the distance from a star where liquid water can exist on a planet's surface. But if thick atmospheres can trap heat, if oceans can exist beneath layers of gas, if life can thrive without sunlight, then the habitable zone becomes less rigid, more flexible, more complex, and potentially much larger. That changes the statistics. Not just how many planets could host life, but how many might already do so. But again, that conclusion is not yet supported by evidence. It is a possibility opened by a single unresolved case. And that is where the story stands. Not at the end, at the edge. Because the next set of observations will either strengthen the case for complex, possibly biological chemistry, or they will reveal a purely physical explanation that resolves the anomaly without invoking life. Both outcomes are valuable. One expands biology, the other expands chemistry. Either way, understanding deepens, and James Webb continues to watch. The next phase of this investigation moves away from detection and into reconstruction. Because once you have a spectrum, once you have those faint dips in starlight, you are left with a harder problem: turning that pattern into a physical world. Not an abstract atmosphere, a place, a system with layers, pressures, temperatures, and flows. And this is where scientists begin building the planet from the outside in. Start at the top of the atmosphere. The outermost layers of K2 18b are exposed to stellar radiation. Ultraviolet photons from the red dwarf star interact with hydrogen, methane, and other molecules, breaking them apart and triggering cascades of chemical reactions. These upper layers are likely thin, dynamic, and constantly changing. Below that, the atmosphere thickens. Pressure increases. Temperature profiles shift depending on how efficiently heat is transported. Winds may move at speeds far exceeding anything on Earth, redistributing energy across the planet. In hydrogen-rich atmospheres, circulation can be deep and complex, with convection cells that extend thousands of kilometers. Now imagine those layers interacting. Photochemistry at the top feeds into chemical transport downward. Molecules formed in one region are carried into another, where they are altered again. The atmosphere becomes a chemical engine, not a static shell. And somewhere within that engine, Webb is detecting signatures. But to understand where those signatures originate, scientists have to map the vertical structure of the atmosphere. That is not straightforward, because the spectrum Webb observes is an integration over altitude. It combines signals from multiple layers into a single pattern. Disentangling those layers requires modeling how light passes through the atmosphere at different pressures and temperatures. This is called retrieval. Atmospheric retrieval models take the observed spectrum and attempt to infer the most likely distribution of molecules, temperatures, and pressures that would produce it. The models are complex. They include radiative transfer equations, chemical networks, and assumptions about cloud properties. And here is where uncertainty compounds. Different assumptions can lead to different interpretations of the same data. One model might suggest a relatively clear atmosphere with strong methane absorption. Another might include clouds that mute certain features, leading to different inferred abundances. A third might introduce additional molecules that shift the fit in subtle ways. So scientists do not rely on a single model. They run many, thousands of variations, each with slightly different parameters, each evaluated against the data. The result is not a single answer, but a distribution of possible atmospheres, ranked by how well they match the observations. K2 negative, 18b, sits at the intersection of those distributions. Methane appears consistently across models. Carbon dioxide as well. The sulfur-bearing signal appears in some models more strongly than others, depending on assumptions about temperature and cloud structure. And ammonia remains suppressed in most viable solutions. That consistency is what gives the detection its weight, not certainty. Convergence. Now move deeper. If an ocean exists, it would sit beneath layers of atmosphere that may be tens or hundreds of kilometers thick. The pressure at that boundary could be immense. The temperature, depending on greenhouse effects, could allow liquid water or something close to it to persist. But the transition between atmosphere and ocean is not necessarily sharp. In high-pressure environments, water can enter supercritical phases, where it behaves neither like a typical liquid nor a gas. In such states, chemical reactions can proceed differently. Solubility changes. Reaction rates shift. This matters because it affects how gases move between ocean and atmosphere. On Earth, gases dissolve in oceans, are transported by currents, and are released back into the atmosphere through biological and physical processes. If K2-18b has a similar exchange, then its atmospheric composition is not just a reflection of its air, but of its ocean as well. Now imagine that exchange happening at planetary scale. No continents to interrupt circulation, no shallow seas, just a global system, potentially mixing chemicals over vast distances and depths. If life exists in that ocean, its byproducts could be distributed widely, not confined to localized regions. That could make atmospheric detection easier, but it could also dilute signals, depending on production rates and mixing efficiency. Again, multiple possibilities. Now, consider energy sources. Life requires energy. On Earth, the primary source is sunlight, but deep-sea ecosystems rely on chemical energy, often derived from interactions between water and rock, or from hydrothermal vents. For K2-18b, several energy pathways are possible. Stellar radiation provides energy to the upper atmosphere. Gravitational interactions, if present, could generate internal heating. Chemical gradients within the ocean or between ocean and atmosphere could provide additional energy sources. The key question is whether these sources are sufficient to sustain complex, self-organizing chemistry, not just reactions, systems, and that question cannot be answered directly from current data, but it can be approached indirectly, by looking for signs of sustained disequilibrium, by looking for molecules that require continuous production, by looking for patterns that resist simple physical explanations. That is what Webb is doing. Now shift to the signal itself again. Dimethyl sulfide, if confirmed, would be one of the first molecules detected in an exoplanet atmosphere that has a strong association with life on Earth. But association is not identity. DMS is a product of specific metabolic pathways in marine microorganisms. It is not a universal marker of life. It is one example of how life can interact with its environment. If life exists on K2-18b, it may not produce DMS at all, or it may produce it through entirely different mechanisms. Or the signal Webb is detecting may not be DMS, but another molecule with a similar spectral signature. This is why follow-up observations focus on broader spectral coverage. Different molecules absorb at different wavelengths. By extending observations into additional bands, scientists can test whether the signal matches DMS across its full spectral profile, or whether it diverges in ways that indicate a different compound. This is a fingerprint test. Partial matches are not enough. Full matches are required. And even then, context matters. Now, consider the role of pressure. At higher pressures, spectral lines broaden. Molecules interact more frequently, altering absorption features. This can make identification more difficult, especially when signals are weak. K2-18b's atmosphere is likely under higher pressure than Earth's, particularly at deeper layers. That means the spectral features Webb observes are shaped not just by composition, but by pressure conditions. Retrieval models attempt to account for this, but uncertainties remain, and those uncertainties propagate into the interpretation of every molecule. Now, bring in another observational constraint: transit depth variations. As K2-18b passes in front of its star, the amount of light blocked depends not just on the planet's size, but on its atmospheric opacity at different wavelengths. By measuring how the transit depth changes across wavelengths, scientists infer which molecules are absorbing light. This method is powerful, but it is also sensitive to stellar noise. Red dwarf stars can have spots, flares, and variability that affect the observed light curve. If not properly accounted for, these effects can mimic or obscure atmospheric signals. So parallel observations of the star are essential, monitoring its activity, characterizing its variability, ensuring that what is attributed to the planet is not actually coming from the star. This is the level of detail required, because the claim being investigated is not small. It is the possibility that life, or at least lifelike chemistry, exists on a planet beyond our solar system, and that claim demands evidence that survives every alternative explanation. Now step back again. We are looking at a world we cannot see directly. We are inferring its properties from light that has passed through its atmosphere. We are interpreting patterns that exist at the edge of detectability, and we are trying to distinguish between biology and physics, using tools that are only just capable of making the measurement. That is the situation, and yet, even within those constraints, the data is strong enough to sustain this investigation. That alone is significant, because for most of human history, the question of life beyond Earth was philosophical. Now it is observational, not answered, but measurable, and K2-18b is one of the first places where that measurement has produced something that does not resolve easily. The next observations will refine the spectrum. The next models will test new combinations of chemistry. The next debates will sharpen the interpretation, and somewhere in that process, one explanation will begin to dominate, or a new one will emerge. That possibility, a new explanation, is not a side note. It may be the most important outcome of all, because history suggests that when astronomy reaches the edge of its instruments, the universe rarely offers a clean answer in the language we expected. It offers something that forces the language to expand. K2-18b may become the first exoplanet where a biosignature was debated seriously enough to change how the field defines evidence. Even if the final answer turns out not to be biological, the standards being forged around this case will shape every atmospheric life detection claim that follows. And those standards are becoming sharper. The first is replication across instruments. A real signal should not depend on one observational mode, one analysis pipeline, or one statistical assumption. It should appear when different instruments observe the same transit in different wavelength bands. It should survive reprocessing. It should remain when different teams use different retrieval frameworks. That is why the argument over K2-18b has been productive rather than destructive. Competing teams are not just disagreeing, they are stress testing the claim. One group emphasizes that the sulfur-bearing signal strengthens when broader wavelength coverage is included. Another emphasizes that the same region of the spectrum may be explained by alternative molecules under different atmospheric assumptions. Both are contributing to the same goal, identifying what kind of evidence is robust enough to carry the weight of possible life. The second standard is chemical exclusivity. A molecule is only useful as a biosignature if the non-biological ways to produce it are constrained well enough that biology becomes the better explanation, not merely one explanation among many. This is where sulfur chemistry becomes so difficult. On Earth, dimethyl sulfide is deeply suggestive because it is so strongly tied to life. But on K2-18b, we do not yet know the full inventory of abiotic sulfur pathways available under hydrogen-dominated conditions, different pressures, different temperatures, and possibly radically different ocean chemistry. That ignorance cuts both ways. It prevents overclaiming, but it also means that the absence of a known abiotic pathway is not the same as proof of biology. The third standard is environmental plausibility. Even if a molecule is detected cleanly, the planet still has to be the kind of place where the proposed source makes sense. This is why the debate over whether K2-18b is truly Haitian or instead a mini Neptune matters so much. A sulfur-bearing molecule in the atmosphere of a deep gaseous world with no accessible liquid water means one thing. The same molecule above a global ocean means another. Environment changes interpretation, and right now, environment is still what scientists are trying to reconstruct. Now consider how narrow the window for interpretation can be. A slight shift in estimated atmospheric pressure changes line broadening. A slightly different cloud deck changes the apparent abundance of methane. A revised estimate of stellar ultraviolet output changes photochemical rates. A better interior model changes whether liquid water is stable at the relevant depths. The entire case moves because every layer of the system is linked. That is why this discovery feels less like finding an answer and more like opening a locked room. Every new key reveals another door. Now bring in habitability more directly. The phrase habitable zone is often misunderstood. It does not mean a planet in that zone is habitable. It means only that, under some assumptions, liquid water could exist. Earth is in the habitable zone. Venus is too near the inner edge and became a furnace. Mars sits near the outer region and lost most of its atmosphere. Distance from a star is not destiny. For K2-18b, habitability is even more conditional. Its orbit places it in the temperate zone of its red dwarf. That is true, but whether that translates into conditions compatible with life depends on atmospheric thickness, greenhouse strength, cloud behavior, ocean stability, and internal structure. Too much atmosphere and pressures become extreme. Too little and heat retention fails. Too much stellar activity and chemistry becomes hostile. Too little mixing, and the atmosphere may not reflect the deeper environment at all. Habitability is a balance, and the reason K2-18b matters is that it may represent a balance point never observed before in detail. Not Earth-like, not clearly uninhabitable, something in between. That in-between category could turn out to be one of the most common habitats in the galaxy, or one of the most deceptive. We do not know yet. Now think about Europa, Enceladus, and Titan again. These worlds taught scientists an important lesson. Life does not need to sit on a sunlit surface. It may emerge in dark oceans beneath ice, in environments shaped by chemistry rather than daylight. That realization expanded astrobiology beyond the old Earth clone model. K2-18b pushes that expansion farther. It suggests that entire classes of planets, once dismissed as too large or too gaseous, may still deserve biological attention. especially if they host ocean-atmosphere interfaces and persistent chemical disequilibrium. But it also raises a warning. The more alien the world, the less reliable Earth analogy becomes. A sulfur-bearing gas on Earth points toward marine biology. A sulfur-bearing gas on a hydrogen-wrapped sub-Neptune may point toward biology, or toward a kind of planetary chemistry Earth never had the chance to produce. That is the edge science is working on now. Now consider the statistical debate more carefully. Public discussion often treats statistics as a simple ladder. 1 sigma weak, 3 sigma interesting, 5 sigma discovery. But in atmospheric retrieval, significance is not always a clean universal number. It depends on model comparison, priors, treatment of noise, and whether the candidate molecule is being tested against a realistic set of alternatives. In other words, a 3 sigma hint can be more meaningful than it sounds, or less meaningful, depending on what exactly was compared. That is why some teams remain cautious, even when a result appears suggestive. The number alone is not enough. Scientists want robustness across assumptions. They want the signal to survive hostile analysis, and K2 negative 18b has now entered that phase. Hostile in the best scientific sense. Every assumption challenged, every alternative tested, every ambiguity exposed. That is not weakness. That is the only way a claim of this scale can become trustworthy. Now shift to what future observations may actually reveal. If Webb continues observing K2 negative 18b and the sulfur-bearing feature strengthens across multiple transits, the next goal will be discrimination between DMS and DMDS and any other overlapping candidates. These molecules have distinct absorption behavior across wider spectral regions. Better data could separate them. If a convincing sulfur molecule remains, attention will turn to abundance. How much is there? Too little, and small abiotic pathways may be enough. Too much, and non-biological explanations become more strained. Then comes the next question: what else is present alongside it? Are there photochemical byproducts expected from abiotic sulfur chemistry? Are there missing companion gases that should exist if the source were geological or atmospheric rather than biological? Is methane present at a level consistent with steady replenishment? Is ammonia still absent? Every answer tightens the net, and eventually the field may reach a point where the correct statement is no longer possible signs of life, but something more precise and more powerful. An atmosphere showing a combination of molecules, best explained by biological activity, pending independent confirmation. That sentence would not sound dramatic, but it would be one of the most consequential sentences in the history of science. And even that would not be the end, because once one world becomes plausible, many others move higher on the list. The search broadens. The Drake equation shifts, not by solving itself, but by losing one of its largest uncertainties. The fraction of worlds that develop life would no longer be pure abstraction. It would have a lower bound greater than one world out of one known habitable example. That changes the emotional geometry of the universe. Not civilization, not contact, life. Even microbial life on a distant ocean world would mean biology is not a singular accident isolated to Earth. It would mean the universe crosses from chemistry into living systems more than once. That is the threshold hidden inside this debate. Now step into the human side for a moment. Astronomers are trained to be cautious, but they are not immune to awe. Somewhere in the process of analyzing those spectra, researchers knew what they were looking at. Not proof, not a headline. A possibility with enough weight to alter careers, fields, maybe textbooks. That kind of moment does not usually look cinematic. It looks like rerunning code, checking line lists, comparing retrieval outputs, writing a sentence, deleting it, writing it again with more caution, forwarding a plot to a colleague with a short message that usually means, "Tell me why this is wrong." And when the colleague cannot kill it easily, the room changes. Quietly, because scientists know the most dangerous moment in discovery is not when the data first appears. It is when you start wanting it to be true. That is why the skepticism around K-18b is not something to get around. It is part of the discovery itself. If this signal survives, it will survive because people tried hard to break it. And that is exactly how it should be. What comes next is not about a single planet anymore. It is about turning one anomaly into a framework. Because if K-18b has forced scientists to refine what counts as evidence for life, then the next step is applying that framework to other worlds systematically, repeatedly, and without bias. And those worlds are already waiting. The catalogue of exoplanets has grown into the thousands. Among them are dozens of sub-Neptune and super-Earth planets orbiting within the temperate zones of their stars. Many of them were discovered by missions like Kepler Space Telescope and TESS, Transiting Exoplanet Survey Satellite. But until recently, they were little more than entries in a database. Now, with James Webb Space Telescope, they are becoming targets. And that shift from detection to characterization is one of the most important transitions in modern astronomy, because detection tells you that a planet exists. Characterization tells you what it might be. Now imagine that process scaled across dozens of worlds, different stars, different temperatures, different atmospheric compositions, some with thick clouds, some with clearer skies, some closer to their stars, some farther away, each one providing a data point, each one either reinforcing or weakening the patterns seen in K-18b. If similar chemical combinations appear again, methane, carbon dioxide, and sulfur-bearing molecules in hydrogen-rich atmospheres, then the argument begins to move from anomaly to class. A class of planets with shared chemistry, a class that demands explanation, and that is how science moves from curiosity to category. But there is another layer, because not all stars are the same. K-18b orbits a red dwarf. These stars are the most common in the galaxy, making up roughly 70–75% of all stars. That alone makes them important. If life can emerge around red dwarfs, then the number of potentially life-bearing worlds increases dramatically. But red dwarfs are also challenging environments. They are prone to flares. Their habitable zones are close in, meaning planets are often tidally locked, one side permanently facing the star, the other in darkness. Atmospheric circulation on such worlds becomes critical. Heat must be redistributed. Chemistry must survive radiation. Clouds may form in ways very different from Earth. So if K-18b turns out to host a stable atmosphere with persistent complex molecules, it suggests that even under these conditions, planetary systems can maintain environments that are not immediately hostile to complex chemistry. That is not proof of life, but it is proof of resilience. Now consider what future instruments will add to this picture. The extremely large telescope, currently under construction, will have a primary mirror nearly 39 meters across. Its light-gathering power will allow for higher resolution spectroscopy than Webb can achieve in some regimes. That means finer detail in spectral lines, better discrimination between overlapping molecules, more precise measurements of atmospheric composition. At the same time, the Nancy Grace Roman Space Telescope will survey large regions of the sky, identifying new exoplanet candidates and providing statistical context. And beyond that, concepts for future missions are already being developed. Space-based observatories designed specifically to detect biosignatures, telescopes capable of direct imaging of Earth-sized planets, instruments that could, in principle, separate the light of a planet from its star and analyze it without relying on transits at all. Each step reduces uncertainty. Each step moves the field from inference toward clarity. But even with all of that, there are limits. Distance is 1 K. K-18b is 124 light-years away. Even if life is confirmed there, it remains observational. We will not send probes. We will not sample its ocean. We will not see its surface directly with current technology. Time is another. Every observation we make is delayed. We are seeing the planet as it was more than a century ago. Any changes that have occurred since are invisible to us for now. And then there is the deeper limit, interpretation. Even with perfect data, we are still interpreting chemistry through the lens of a single example of life our own. That lens is powerful, but it is not universal, which brings the story back to where it began. A signal, a pattern in light, a set of molecules that do not settle into something simple, and a question that remains open. What is producing them? Now connect that to the broader cosmic context. For decades, the search for life beyond Earth focused on radio signals, listening for intelligence, searching for patterns that could not be explained by natural processes. That search, tied to the Fermi paradox, asked a different kind of question. Not, is life common, but where is everyone? K2-18b shifts the focus. It brings the question closer, simpler, more fundamental. Not intelligence, life, because before civilizations, before communication, before technology, there is chemistry that crosses a threshold from non-living to living. And that threshold may leave traces in atmospheres, in oceans, in the balance of molecules that refuse to settle into equilibrium. If those traces can be detected, then the silence of the sky changes meaning. It no longer implies absence. It implies distance, limitation, and the difficulty of detection. Now imagine the implications if K2-18b or a similar world eventually crosses the line from possible to probable. Not a single announcement, but a convergence of evidence. Multiples molécules, multiples observations, multiple independent teams reaching the same conclusion. At that point, the discovery would not be loud, it would be precise, and its impact would not be immediate spectacle. It would be gradual realization that the universe produces life, not once, more than once. And if that is true, then the Drake equation does not collapse into a single solution. It opens. The fraction of life-bearing worlds becomes greater than zero in a measurable way. The galaxy becomes less empty in principle, even if it remains quiet in practice. Now return to the present, because we are not at that point yet. The signal is still being tested. The molecules are still being debated. The models are still being refined, and Webb is still collecting light. Each photon carrying information from a distant world, each observation adding another layer, each analysis pushing the question forward. And somewhere in that process, the answer is waiting, not as a sudden revelation, but as a pattern that becomes too consistent to ignore, a pattern that survives skepticism, a pattern that fits better than its alternatives, until what remains is not certainty in the absolute sense, but confidence strong enough to change how we understand our place in the universe. That moment has not arrived, but it is closer than it has ever been, and K2-18b is one of the places where that distance is being measured. And that distance, the gap between what we suspect and what we can prove, is where the final layer of this story unfolds. Because in astronomy, discoveries are rarely about a single object. They are about thresholds. K2-18b sits at one of those thresholds. Not the first exoplanet discovered, not the first with an atmosphere, not even the first where complex molecules have been detected, but the first where the combination of environment, chemistry, and observational capability has brought the question of life out of speculation and into measurable tension. That tension is what defines this moment, because for the first time, we are not asking whether we can detect atmospheres. We are asking whether we can distinguish biology from chemistry across interstellar distances. And that is a fundamentally different challenge. It requires more than better telescopes. It requires a deeper understanding of planetary systems as complete environments. Now consider how fragile that distinction is. A single molecule, even one strongly associated with life, is not enough. A combination of molecules is stronger, but still not definitive. What scientists are ultimately looking for is a network, a chemical system that is self-consistent, persistent, and difficult to reproduce without invoking processes that maintain it over time. That is what life does. It maintains patterns, against entropy, against equilibrium, and that is what makes atmospheric biosignatures so difficult to confirm. Because the atmosphere is not the source. It is the surface expression of deeper processes that we cannot see directly. Now imagine the moment when enough evidence accumulates, not a press release, not a single graph, but a body of work, years of observations, dozens of papers, independent analyses converging. At some point, the language will change, from possible to consistent with, to something stronger, and even then, the scientific community will resist finality, because finality is not how science operates. It operates through confidence, through models that survive testing, through explanations that outcompete alternatives. If K-18b reaches that point, it will not be because the data became perfect. It will be because every other explanation became less convincing. Now step beyond the planet itself, because the real impact of this discovery is not confined to one world. It is about what kind of universe we live in. For most of human history, life was a singular fact. Earth was the only known example. Every theory of life, every assumption about its origin, every model of its requirements was built on that single case. Now that foundation is being tested, not overturned, but expanded. If life exists on K-18b or on any similar world, then life is not an isolated outcome. It is a process that can occur under multiple conditions. That realization changes how we think about everything that follows. Evolution, complexity, high intelligence, not guaranteed, but no longer unique by default. And yet, even if life is common, communication may not be. Civilizations may be rare, signals may be faint, distances may remain too vast. The Fermi paradox does not disappear, it evolves. The question shifts from, is life out there, to, how often does life become something that can be detected across the void? K-18b does not answer that, but it moves the first part of the question closer to resolution. Now return to Webb. Floating at the Lagrange point 2, shielded from heat, operating in the cold darkness, it continues to do exactly what it was designed to do: collect light, ancient light, light that has traveled for more than a century across interstellar space, light that carries, encoded within it, the chemical state of a distant world. Every observation is a reconstruction. Every spectrum is an interpretation. And yet, through that process, the invisible becomes measurable. Now, imagine what Webb will see in the coming years. More transits of K-18b, more data on similar planets, more surprise. Because if there is one consistent lesson from Webb so far, it is this: the universe is more efficient, more complex, and more willing to produce unexpected structures than our models predicted. Massive galaxies forming too early, black holes growing too fast, and now, possibly, atmospheres that hint at processes we do not yet fully understand. K-18b fits that pattern, not as an isolated anomaly, but as part of a broader shift. A shift from a universe that was largely theoretical at large scales to one that is increasingly observed in detail, and detail is where assumptions break. Now consider the final constraint: time. Not the time it takes light to travel, but the time it takes for science to converge. This discovery will not resolve in a single year. It may take a decade. New data, new models, new instruments, each step reducing uncertainty, each step narrowing possibilities, until eventually the question is no longer open in the same way. But even then, something remains, because even if we confirm life on another world, we will still not know how often it happens. We will still not know how it begins. We will still not know how it evolves under different conditions. Each answer opens more questions. That is the nature of this field. Now, bring everything back to the present moment. A planet 124 light-years away, a red dwarf star, an atmosphere containing methane and carbon dioxide, a tentative signal of sulfur-bearing molecules, an absence of ammonia that suggests something is altering the chemistry, a possible ocean beneath a hydrogen-rich sky, and a telescope capable of detecting all of it from across interstellar space. That is where we are, not at confirmation, not at dismissal, at investigation. And that investigation is one of the most precise, most cautious, and most consequential ever undertaken. Because the outcome, whatever it is, will redefine a boundary between chemistry and biology, between expectation and observation, between being alone and not. And Webb is still watching, still collecting, still building the dataset that will eventually tip the balance one way or the other. Whatever is happening on K/18b has been happening for millions, perhaps billions of years. We are only now beginning to see it. And whatever the final answer turns out to be, it will not just tell us about that world. It will tell us something about the universe itself. And that final answer, when it comes, will not arrive as a single moment. It will arrive as a threshold quietly crossed. Because by the time scientists are willing to say that biology is the best explanation for an atmosphere 124 light-years away, the evidence will have already accumulated beyond a point where reversal is likely. The debate will not disappear, but it will narrow. The range of plausible alternatives will shrink until one explanation stands taller than the rest. That is how this ends. But before that happens, there is one more layer that has to be understood. Uncertainty itself, not as a weakness, as a structure. Every measurement Webb makes carries uncertainty. Every model introduces assumptions. Every interpretation depends on what is included and what is left out. These uncertainties are not noise to be eliminated. They are boundaries that define how far a conclusion can go. In the case of K/18b, those boundaries are still wide. We do not yet know the exact pressure at the base of the atmosphere. We do not know the precise temperature gradient from top to bottom. We do not know the detailed cloud structure, or how thick those clouds are, or how they vary across the planet. We do not know whether the ocean, if it exists, is accessible to the atmosphere in a way that would allow chemical exchange. We do not know whether the sulfur-bearing signal is truly dimethyl sulfide, dimethyl disulfide, or something else entirely. And we do not know whether any of the detected molecules are being produced by life, by chemistry, or by processes we have not yet imagined. Those unknowns are not obstacles. They are the map, because each one points to a specific observation, a specific model, or a specific experiment that can reduce it. That is what the next decade of research will do. Now consider what a resolved version of this system might look like. Not in imagery, in data, a spectrum with higher resolution, where overlapping molecular signatures separate cleanly, multiple transits showing consistent patterns across time, independent instruments confirming the same features in different wavelength ranges, a refined atmospheric model that fits all observations without requiring extreme or unlikely assumptions, a set of molecules whose coexistence is best explained by a sustained non-equilibrium process, and a set of alternative explanations that fail to reproduce the full dataset simultaneously. That is the endpoint of this investigation. Not certainty in the absolute sense, but convergence strong enough to support a conclusion. And if that conclusion points toward biology, even cautiously, it will mark a turning point, not because it answers every question, but because it answers the first one. Life exists beyond Earth. Now, shift perspective again, because while this discovery is unfolding at the edge of our instruments, it is also unfolding at the edge of our understanding. For centuries, the question of life beyond Earth was constrained by what we could see: planets in our own solar system, surfaces we could map, environments we could probe directly. Now, we are extending that search to worlds we cannot visit, cannot image directly, and cannot sample. We are inferring life from light, from chemistry, from patterns that exist at the threshold of detectability. That is a new kind of science, and it requires a new kind of caution, because the cost of being wrong is not just scientific, it is conceptual. A premature claim of life would reshape expectations, funding, and public understanding in ways that are difficult to reverse. That is why the standard for evidence is so high, and why it should be. Now, return to the molecules one last time. Methane, carbon dioxide, a possible sulfur-bearing compound, an absence of ammonia. Individually, none of these proves anything. Together, they form a system that does not settle easily into a purely physical explanation. That is why K-18b matters. Not because it confirms life, because it challenges simplicity. And challenges in science are not problems to be avoided. They are signals that something deeper is waiting to be understood. Now consider what happens if the final answer is not biological. If future observations show that the sulfur signal disappears, or is explained by an unexpected abiotic pathway, or that the planet's environment is too extreme for life as we understand it, that outcome would still be significant. Because it would expand our knowledge of planetary chemistry, it would reveal new processes, new pathways, new ways that atmospheres can organize themselves without life, and that knowledge would feed directly back into the search, making future detections more precise, reducing false positives, refining the criteria for what counts as a biosignature. In other words, even a negative result moves the field forward. Now imagine the opposite. The signal strengthens, the molecules align, the models converge, and the remaining explanations narrow to a point where biology becomes the most consistent interpretation. That outcome would not just answer a question, it would open an entirely new field, comparative astrobiology, the study of life across different planetary environments, not just how life begins, but how it adapts to different chemistries, different pressures, different energy sources. And that field would not be theoretical, it would be observational, driven by data from worlds like K-18b. Now step back for the final time, because everything in this story leads to a single point. A boundary on one side, chemistry on the other, biology. For most of human history, that boundary was invisible beyond Earth. Now it is being probed, not directly, but through the light of distant stars, through the atmospheres of planets we cannot touch, through the patterns those atmospheres leave behind. K-18b is one of the first places where that boundary might be crossed, or where we might learn how difficult it is to cross at all. And that is the real significance of this discovery. Not the headline, not the possibility, the process, the slow, careful, cumulative movement from uncertainty toward understanding. And James Webb, cold and silent in deep space, continues to do what it was built to do. Watch, measure, record, and wait, because whatever is happening on that distant ocean world has been happening for longer than human civilization has existed. We are only just beginning to see it, and whatever the answer turns out to be, it is already written in the light that is still on its way to us. And there is one final piece that completes this picture. Not a molecule, not a model, a limit, because even as Webb pushes the boundaries of what we can detect, it also defines the edge of what we can know. K-18b is 124 light-years away. Every spectrum we analyze is already history. We are not observing the planet as it is now. We are observing it as it was when that light left its atmosphere, when those molecules absorbed those wavelengths, when that chemical balance existed in a moment long gone. That delay is unavoidable. It is built into the structure of the universe, and it means that even if we confirm life there, we are confirming life in the past, not necessarily in the present. Now, consider another limit: resolution. Webb cannot see the surface of K-18b. It cannot map its oceans. It cannot detect continents, if they exist, or currents, or weather systems in detail. Everything we know comes from integrated signals, averaged across the planet, blended across layers, compressed into patterns of light. That means there are questions we may never answer directly. What does the ocean look like? How deep is it? Is it calm or turbulent? Does it host localized ecosystems, or is it chemically uniform? Those details are beyond current observation. And yet, even without them, the larger question remains accessible, because life, if it exists, leaves traces, not in image, in chemistry, and chemistry is what Webb can measure. Now imagine the future beyond Webb. Telescopes with even greater sensitivity, instruments designed specifically to isolate planetary light from stellar glare, observatories capable of detecting polarization signatures that might reveal surface properties, spectrometers that can resolve molecular features with precision far beyond what we have today. Each of these advances will reduce uncertainty, but none will eliminate it entirely, because the deeper limit is not technological, it is epistemological. We are trying to infer life from patterns that can be produced by non-life under the right conditions. We are trying to distinguish processes we understand from processes we do not, and we are doing it across distances that prevent direct verification. That is the challenge, and it is why this discovery matters. Not because it solves the problem, because it makes the problem real. Now return to the beginning. A telescope, a distant star, a planet passing in front of it, a fraction of light filtered through an atmosphere, a spectrum, a set of molecules, methane, carbon dioxide, a possible sulfur-bearing compound, an absence of ammonia, each one a piece of a system, each one a clue, and together, something that does not resolve cleanly into a single explanation. That is where the story lives, not in certainty, in tension, because tension is what drives science forward. Now consider what happens next. Webb will continue to observe K2-18b, more transits, more data, higher confidence, or lower. Other telescopes will join. New planets will be studied, patterns will emerge, or they will not. And over time, the question will narrow, from possible signs of life to something more precise, or something more constrained. Either way, the boundary between chemistry and biology will become clearer, and that clarity will extend beyond a single world. It will shape how we interpret every atmospheric signal that follows. Now, step back one final time, because this is not just about K2-18b. It is about the method, the idea that life can be detected remotely, that biology can be inferred from light, that the universe can be read, not just seen. That idea has moved from theory to practice, from speculation to measurement, and K2-18b is one of the first places where that transition is happening, not completed, but underway, and that is enough to change the direction of the field. Because once a question becomes measurable, it stops being philosophical, it becomes scientific, and once it becomes scientific, it becomes solvable. Not immediately, not easily, but eventually. Now hold on to the final image. Not a picture, a process. Photons leaving a distant world, traveling for 124 years, crossing interstellar space, entering a telescope, passing through instruments, becoming data, becoming spectra, becoming models, becoming debate, becoming understanding. That is the chain. And somewhere along that chain, a pattern has emerged that may represent one of the most profound discoveries humanity can make, or one of the most instructive false signals we will ever analyze. Either outcome matters, because both lead to deeper understanding, and that is the real destination. Not just finding life, understanding how to recognize it. And James Webb continues to watch. The light is still coming, the data is still building, and the answer, whatever it is already on its way.